All right, so this is section 9.5. We're going to be talking about the logistic equation. It's actually a form of exponential growth um, with a slight difference. It's called logistic for a reason. Um, we're going to look at it both graphically and algebraically and be able to solve and interpret initial value, logistic value growth problems. It does say on this thing that the homework is in a worksheet. It is not. It is actually something in your web assign. So ignore the fact that that says worksheet right there. All right. Let's see. Previously, we have discussed differential equations using slope fields, which is a graphical representation. Euler's method, which gives us a numerical representation, and separable differential equations, which we carried through into our exponential growth and decay models, and that gives us an algebraic representation. Today, or this lesson, we're going to actually talk about the logistic growth model. So one of the main things is logistic growth model. It looks like it's an exponential in its early stages, so it tends to either grow or decay, looking like an exponential. But then eventually it starts to level itself off, and it approaches this thing which is called a carrying capacity. Carrying capacity. And that typically happens because you have some sort of limited resources. Those resources could vary from, depending on, it could be just about anything, depending on what kind of a situation you have. For smaller populations, so if the population is not large, we can basically use our dp over dt equals kp, where again, k was some kind of a constant of proportionality. That would be your standard exponential growth and decay model. As the populations get large, however, with these logistic growth models, the resources tend to become more limited, and thus the population, once again, it approaches this thing called a carrying capacity. Kind of an important topic there, an important part of this. We're going to call the carrying capacity capital M, which is the maximum population an environment is capable of sustaining in the long run. So think about probably not the uh, best example as far as, I don't know, it's kind of morbid, but think about if you dropped a whole bunch of animals on an island and there was very limited resources, such as, a limited amount of food or whatever on the island, or even just space on the island. Eventually, that that large population of animals is going to start to, unfortunately, either die off or kill itself off or whatever's going to happen. And it's going to level itself out to a sustainable carrying capacity, a sustainable amount of life that can survive on this island given the amount of resources that are there. Again, probably not the best example there, but one of the ones that just typically comes to mind, probably because I have a whole, survivor type mindset when it comes to things like this. So normally, if this was an in-person, I would ask you to give an example of when the carrying capacity of something cannot be exceeded. The easiest way to think about a way a carrying capacity can't be exceeded is if you actually have a limited space. If you think about putting bacteria like in I don't know, a petri dish or something like that, and then you cover it. So you actually have a limited amount of space. It's very much like putting a whole bunch of something that grows in a dome or something like that. Eventually, you're going to run out of space. You have a limited amount of space. So that's where a carrying capacity could not be exceeded. You can exceed a carrying capacity in something like I said, where if you dropped a whole bunch of animals or something on a small island or whatever, that might be over the carrying capacity and it is exceeded. And then eventually it would level itself off due to human nature or just nature itself. Anyway, if you can think of other ones, again, those are kind of real life, or the best that I can come up with, real life example type things. Other than that, so it says here on page 2, the simplest expression for relative growth rate that incorporates these assumptions is 1 over p times dp over dt equals k times the quantity of 1 minus p over m. And I know it says the simplest form. That does not look very simple, but believe it or not, it is. Now, if we actually want to solve for the differential portion of this, the dp over dt, you're simply going to multiply both sides by p. And then you get the equation that is in that box. dp over dt equals kp times parentheses 1 minus p over m. Now remember that the m stood for the carrying capacity, the maximum sustainable capacity. The k is still a constant of some kind, constant of proportionality, and p is your initial population. All right, so to kind of relate it to what we were doing, notice that if p is a really small number, so we're going to let p be a really, really tiny number. Population is going to be small. If that's the case, if the population is small, no matter what m is, m could be 5,000 and p could be, 3. Who knows? Whatever. The smaller you make the population, the closer the p over m becomes to 0. And if that's the case, if this portion right here approaches 0, then the 1 minus 0 on the inside just becomes 1, and then ultimately all you're left with is dp over dt equals kp, because again, this whole piece right here would approach 1, because 1 minus 0 would be 1. Get rid of that. However, as the population, the p-value, starts to approach the carrying capacity. Well, now we're talking again, this is the idea of limits. As p gets closer to m, this piece right here now gets closer and closer to 1. Because as p gets closer and closer to m, that becomes closer to 1, which makes the inside of that parentheses 1 minus 1, which goes to 0. So that means that if p over m approaches 1, then the dp over dt, or the rate of change of the population over time, starts to approach 0, which again, given what I said in the beginning, should make sense, as the population should start to level itself off. The rate of change should start to approach 0. Whether it actually gets to 0 or not depends upon what's actually happening in the problem. So what does all that stuff mean? In general, as the population gets closer to its carrying capacity, the growth rate starts to slow down. So what happens to the growth rate if the population exceeds the carrying capacity? I'm going to kind of show it to you in a very, very simplified graphical model. So up here somewhere, we're going to call our carrying capacity, which is m. Okay, up here is our carrying capacity. Again, this is what is sustainable in the long run. So in the beginning, it's not that big of a deal, but eventually it will have to approach that. Again, it's the idea of a limit. It's a horizontal asymptote. A limit as something approaches infinity. We will start off with the idea that our initial population, we'll call this p sub 0 for p initial, is there. A couple of different possibilities. One, again, this is going to start to grow. Your population is going to start to grow. It's going to look exponential in the beginning, and then it's going to start to level itself off as we get closer and closer to m. So it'll start to grow exponentially, and then at some point it's going to start to level itself off and approach our carrying capacity as we go further and further out. That is one possibility. Another one of our possibilities is that the population could grow pretty fast in the beginning and actually exceed the m value, the maximum sustainable capacity. And if that happens, again, it's going to start off exponential. It's going to grow pretty fast. All of a sudden, it's going to get actually above the m, but what's going to happen is over time, this thing actually has to come back down, and it'll dip just below m and then start to level itself off right around that carrying capacity. Now remember, it's very difficult for me to draw, but the arrow as this thing goes off towards infinity, towards the right, is so infinitely close to m, there's basically not a difference there. It's just really hard to draw that. Now there is a possibility, and I don't have it on this one, I'll show it on the next page, where you could actually have something where the population starts above the carrying capacity and then it's going to eventually dip down below. But I didn't really draw that one really well here. So hopefully that makes sense. Now, there is something I want to talk about and touch on real quick here. The maximum growth rate that you're going to have here is always going to be when you are halfway to the carrying capacity, and that's halfway from the initial population to the carrying capacity. So your maximum growth rate, let me go with, let's go with purple. The maximum growth rate of each one of these things is going to occur. That's horrible because I did put that in the wrong spot. I just probably didn't draw this very well, is the problem is. Let's see, let's do the bottom one first. It looks like the maximum growth rate is right about there, which means that the maximum growth rate is going to be right about there. If you kind of want to think about it, it's going to be where your point of inflection is. It's going to be where the concavity changes from concave up to concave down. All right. And that will be at the halfway point between the initial population and the carrying capacity. That's where your maximum growth rate will be. All right, so let's take a look at a graphical representation using a slope field. For the logistic equation, we're given that K equals 0.08. Our carrying capacity is 1,000. The logistic differential equation and slope field is shown below. So we're given the fact that we have a differential equation, dp over dt, equals 0.08p times 1 minus p over 1,000. What you see down here is you see a whole bunch of different initial populations and what the graphs could look like. Try and squeeze all that on there. So you've got one here where it looks like on the bottom that the initial population maybe starts at 100. It starts to grow and then level itself off as it approaches the carrying capacity of 1,000. You've got one where it looks like the growth rate, excuse me, the initial population starts at 400. Once again, it starts to grow and then starts to level itself off as you get closer and closer to 1,000. And then you actually have one where the initial population started at 1,300 is what it looks like on the graph, and then has to come down and dip just below the carrying capacity of 1,000. Now we're only looking at the first quadrant here because negative populations, as it says here, aren't really meaningful in this circumstance, and we're only interested in what happens after time 0 in this case. So you kind of look at what's going on. Look at the slopes when the population is less than the carrying capacity. What do all those slopes look like? Well, when the population is less than the carrying capacity, even though it starts to level off, all of the slopes are positive. Okay, they are all increasing. They're increasing very slowly as we get further and further out to the right, more time goes on, but they are still technically increasing. And then if you look at what happens as the population has exceeded the carrying capacity, because again, it's got to come back down to where the carrying capacity is, all those slopes are going to be negative because the function or the equation has to come back down. And ultimately, as we've talked about, as time goes on, the slopes tend to get less steep. Might be the easiest way to say that. They tend to level off, and they start to approach 0. All right, hopefully that makes some kind of sense, at least graphically, as to what we're looking at there. Now the question is, these are differential equations. Is there a way to get from this differential equation, maybe the one that's here, and get back to an actual population equation so that it's a population at some particular point in time? And the answer, of course, is yes, that there is. And we're actually going to stop this video here because the next one it's a little bit long in order to show it. What we're going to do is we are going to take, previous page, we are going to take this equation and we're going to solve that for P. And this is the reason that we do this specific lesson after We've done all the separable differential equations because that's what this is. This is a separable differential equation, and it's going to incorporate some antiderivative techniques that we need to use from prior lessons, from chapter 7 stuff. All right, so we're going to stop this video here. We're going to come back. We're going to basically prove and solve for the population equation, and then we will do the problems on the last page to show what it is that you should be looking for in solving these problems.